once in a while, we're just going to go through and we'll read the section in the textbook because that's a really valuable skill. So what I've got there is a copy for you of the, I think there are 8 pages in 1.3. We're going to read through this and we're going to make sure we understand it. There are parts of this book that are really well explained, some parts that maybe not so much. And what typically happens in a math textbook is, because it has to be so mathematically precise, I mean, some great math professor wouldn't want to send something out to his colleagues that wasn't all mathematically rigorous and correct and stuff like that. There might be a little bit too much technicality in there, and they may skip some steps because the book is big enough as it is. If they showed every single step, it would probably be twice the size, okay? So we want to be able to read through a textbook and understand what that person is trying to say. That's part of understanding other people's arguments and picking them apart and being able to see why they're logically correct or something like that. Okay, so this section is on Introduction to Functions, and here's what we're going to do. I'm just going to go around. We'll kind of jump around a little bit. I'll ask people to read things and see what we've got here. Again, notice the margins. It talks about what you should learn, why you should learn it, and things like that. Hopefully by the time we're done, I'm not saying we're not going to read any of those, but I would definitely, if we don't read them, I would read them on your own. So Raymond, would you start right there and read that first paragraph? Nice and loud.
Many everyday phenomena involve two quantities that are related to each other by some rule of quantics. But the mathematical term for such a rule of quantics is a relation.
Okay, so the word here is relation, and it's talking about something called a correspondence. Now, we're going to use these words several times, so I would make sure you know what they are. We're going to say that these numbers correspond to each other, and they use the word relation because there's some relationship between the two of them, okay? It's not that they picked these words from random and, well, I know what a relation is, but why would they use the word here? Okay, it actually has a meaning. There's some sort of relationship or something that relates these two variables. Okay, so the first one says the simple interest I, or we could just say the interest earned on $1,000 for 1 year is related to the annual interest rate, which we use the letter R. Okay, no surprise there, R for interest rate. Okay, and the formula I equals 1,000 times R. So they're just giving a formula there. So if you know the interest rate, you put in $1,000. If you know the interest rate, you can figure out how much interest you earned on that. Okay, so put $1,000 in the bank, see how much you get when you're done. Okay, this is one that you should be familiar with. The area of a circle is related to, there's that word again. So you can figure out what the area of the circle is because it's related to the radius by this formula right here. The area is pi times r squared. Okay, so these are examples of relations. Okay. Noah, would you read that next paragraph, please? Okay, so they've given a couple of examples, and then they said, hey, we've got this special case right here. It says it matches one item from one set with exactly one item from a different set. Okay, so there's this nice relationship, very specific relationship, and we call that relationship a function, and then they've got a definition right here. Okay, so let's take a look at the definition, and I'm going to read this. Okay, it says a function f, so just naming the function, okay, from set A to set B is a relation that assigns each element x in the set A to exactly one element in y from the set B. This set is the domain of inputs of the function, and the set B is the range of the set of outputs. Okay, very mathematical, very wordy. Okay, here's what we're talking about here. Each, write this down please, each x corresponds with only one y. The x's, they're the domain, and the y's, they're the range. So we're going to take that big definition right there, and we're going to summarize it, and we're going to say each x corresponds with only one y. Each x can correspond with only one y. The x's make up a set that we call the domain, and the y's make up a set that we call the range. Now, if you don't know how to keep those straight or haven't got those straight yet, how many of you have heard those words before? Domain and range? Very good. Okay. X and Y is alphabetical. Domain and range is alphabetical. So if you ever have to think, just think alphabetical. X, Y, domain, range. X is domain, range is Y. Okay. And then it shows us a figure that shows a relation, maybe a function. It says to help understand this definition, look at the function. So it says this is a function. So what we want to notice over here is this is the set of x's or the domain. It says domain right here. And these are the inputs. These are what we're going to put in. This is the time of day. We'll assume that this is 1 o'clock, 2 o'clock, 3 o'clock, and so forth. Over here are a bunch of temperatures. So 1 corresponds to 9. We'll assume that's Celsius, and it is. Okay. 2 o'clock corresponds to 13. 4 o'clock corresponds to 15. 3 o'clock corresponds to 15. 5 corresponds to 12. And 6 corresponds to 10. Doesn't matter that a couple of these are not used. Okay. Think very carefully. Do each one of the x correspond to only one of the y's? Do each one of these correspond to only one over here? You know, I see a couple people shaking their head yes, and I see a couple people, no, I don't think so. And the issue would be right here. Okay, if you're looking at something and thinking there's a problem, it's right here. Now what we said was each x can correspond to only one y. In other words, each time of day can correspond to only one temperature. Take a good look. Does that correspond to only one temperature? Yes, it does. Does that one? Yes. This one? 4 o'clock only corresponds to 15 degrees. Does it matter that 3 o'clock also corresponds to 15 degrees? It doesn't. Okay, this is a function. Okay, the definition says each x can correspond to only one y. It doesn't say each y can correspond to only one x. This would be a problem, and think about this in terms of the temperature. What does 4 o'clock correspond to? Corresponds to 9 degrees, and it corresponds to 15 degrees. What's the problem with that? Yeah, you can't have two different temperatures for the same time of day, right? Can't have two different temperatures for the same time of day, okay? So there's the problem. This is okay. That's not. And if I said, you know what, hey, at 1 o'clock it was 9 degrees and it was also 12 degrees. Doesn't work that way. Not in the same place. Okay? So this is what we call a mapping, or we call a graphical correspondence. We're actually drawing lines to show what corresponds to what. We can also write it down as a set of ordered pairs. Okay, and you'll notice that in each ordered pair, the first coordinate is the input and the second coordinate is the output. Okay, so in each one of these, we had time of day and then temperature. Okay, take a good look at these two. This is where we had the issue. 3 corresponds to 15 and 4 corresponds to 15. Is it possible? What if they were all 15 degrees? Would that be okay? Could it be a steady temperature the whole day? It doesn't happen very often. Okay, but that could happen. Okay, it's that each x can correspond to only one y, not the other way around that makes a function. Okay? All right. And then it says, note the following characteristics of a function. Okay, Cameron, would you read those 3? Okay, that's good. This is the important one here. 2 or more elements of A, so you can have a couple x's go to exactly the same y. And that's that part that we were talking about there. Okay? And then it says the converse of the third statement. Does anybody know what a converse is? Anybody heard that before? Converse is like switch it around. Okay? Go the other direction. Okay? So what that means is we can't have one element here, sorry, two elements here go to the same one here. All right? So an element in A cannot be matched with two different elements of B. Okay, go ahead and flip to that next page, or let's see, I copied that off so it was on the same page. And then we're going to go through a couple of descriptions of ways that we can represent a function. And let's see, Tara, would you read those four nice and loud, please? Okay, hold on one second. So the first thing we can do is we can describe it verbally. We can talk about what it is. We could write down what it is. What's the next one? Okay, so that's kind of what we did just a second ago. We can do it numerically. We can just show this number matches up with this number matches up with that number. Next one. Okay, very good. So we could graph that on a plane, and notice what they said here. The input are the horizontal axis. Those are usually the x's, and the output, those are the y-axis. Those are the vertical axis. And then the last one? Okay, so algebraically, using an equation that relates the two variables. Okay, these come up all the time, and these are things that we're pretty used to. Numerically is not too terribly bad because they'll give you all of the numbers. Verbally is usually where people struggle, because that's where we have maybe a story problem type of thing or a description of what that relationship is, and we've got to translate it into an equation or be able to graph it. Okay, so the next part says we're going to be testing functions, and it says in the following example, you're asked to decide whether or not the given relation is a function. Does each x correspond with only one y? Okay, so to do this, you must decide whether each input value is matched with exactly one output value. Okay, if any input value is matched with two or more output values, then that relation is not a function. So let's take a good look at this. And again, they've got the answers below, so kind of avert your eyes to looking at this. It says the input is the number of representatives from a state, and the output is the y value is the number of senators. Okay, got to have a little background knowledge here. Okay, how do you determine how many representatives each state has? Okay, it's based off population. Okay, like California, I think they have 43 representatives. How many does Utah have? We have 4 now. Okay, we used to only have 3. Okay, what about senators from every state? 2. There are 2 from every state. Okay, so there are some states that only have 1 representative, but they have 2 senators. We have 4 and we have 2 senators. California has 43 or something like that, and they have 2 senators. Does each x correspond with only one y? Are there any states that have 2 senators and also have 5 senators? Nope. So is that a function? Yes, it is. Okay. Happens to be called a constant function. Okay. Let's take a look at this one. Okay. This is a numeric relationship. This is how they've described this. This was verbal. This was in words. Let's take a look at this one, and can you see if there's a problem, and if so, where? Logan. 2 corresponds to 11, and it corresponds to 10. We don't like that type of uncertainty. If we plug in a 2, we want to know exactly what the answer is. We don't want to wonder whether or not it's a 10 or an 11. Okay, so this one is no. This is not a function. So not a function. Okay. And then we take a look at this one right here. This is a graphical representation of this relationship. Let's take a look at the x values. The x value here is -2. It corresponds to this number up here, which is 3. That -1 corresponds to 0. 0 corresponds to -1. 1 corresponds to 0, and 2 corresponds to 3. Is that a function? Yes, it is. Okay? Because each one of those x's corresponds to only one y. Now, would it be a function if I had a point straight down here? If 2 also correspond to -1.5? Nope, it wouldn't be. And we're going to talk more about that. Okay? So that one does. Let's see. Tony, would you read that next one where it says representing? Okay, stop right there. Discrete mathematics, okay? Fancy word for math where we're using specific amounts of numbers, okay? Not something you need to worry about. You can actually get a degree in discrete mathematics. So they're just throwing in some extra mathematical language there, okay? Then it says what, Tony? Keep going. No, you're fine. Okay. Now, let's think about that for just a second. You've probably heard a lot of that terminology before. Is that paragraph very difficult to understand? Hopefully not. There are a couple things I want to point out. This is language that's used all the time, so let's make sure we understand what it means so that we're not intimidated by it. The variable y as a function of the variable x. We'll hear that all the time. F is a function of x, y is a function of q, whatever it happens to be. And what that means is you're going to plug in x's and you're going to get out y. The y is determined by what we plug in an x. And that's why x is the independent variable because that's the one that we plug in. Y is the dependent variable because it depends on what we plug in for x. Okay? So if I plug in a 2, I've determined what y is. Y is going to be 4. So the value 4 depended on us plugging in a 2. Okay? That's why we call that dependent and independent. Okay? Let's flip that page over and let's take a look at the next example. It gives equations now. And generally, if we're working with algebraic expressions, algebraic equations, it's slightly more difficult to figure out whether or not we've got a function. Okay? So here's what it says. Which of the equations represents y as a function of x? And then it runs through and it shows you how to do this. So we've got this equation right here and this equation right here. Notice how similar they look. They've both got x's and y's. They've both got a 1. They've both got squares in them somewhere. But let's take a look. When we say, is y a function of x, here's what we're checking for. Determine whether y is a function of x. Solve for y in terms of x. Get the y all by itself, and let's take a look at it. So on this first one, the only thing we have to do is we just have to move the x squared to the other side. Y equals 1 minus x squared. And think for just a second. If I plugged in a number for x, how many answers would I get out? Like if I plugged in a 0, what do I get? Get a 1. What if I plugged in a 2? 1 minus 4, I'd get a negative 3. Is there ever a time where I get 2 answers? Nope. That makes it a function because each x that we plug in is going to give us only one answer coming out, only one y value. Let's take a look at this other one. Same type of thing. We're going to move the x to the other side by adding. Then I'm going to get the y by itself by, what did they do from this line to this line? Took the square root of both sides. And then they realized when we put a square root in a problem, we have to put a plus or a minus, right? So now if I plug in a value, let's say I plug in a 3. So let's say I make a little xy table just so I can plot this and try and figure out what it looks like. I plug in a 3. If I plug in a 3 here, I get 1 plus 3. Then I take the square root. I get 2, but it's got a plus or minus in front of it. If I plug in 1x, how many y's do I get out? 2. Is that a function? No. So y is not a function of x. Okay? It's that plus or minus that screws things up. We only want one answer out, not 2 answers. Okay? Any questions? Okay. Sven, would you read that next paragraph there? Yep. Okay, let's stop right there. All they're saying here is You know, when we started this class, we talked about some notation that we'd use for sums and adding things up and finding averages and coming up with those funky formulas that you might see in statistics. Who? Nope. Nope. All they're saying here is if we're dealing with a function, let's give it a name. So we use f. Why would they choose f? Because f is a function. Okay? Stands for function. That's it. Okay? And we usually use this notation. So the input is x, the output is f of x, or the function value at x. So instead of writing y equals 1 minus x squared, we're just going to say the output is the function value at that particular point, at that particular x value. And we literally say that f of x. And that's what it's saying here. Okay? The value of f at x, or f of x. How many of you have seen function notation before? Very good. Hopefully it shouldn't be a problem here then, right? So let's skip down here. You'll notice that it has this right here. It's got us a new function, and it named it f of x. So we know that's got to be a function. We're going to find f of negative 1. So there are a couple nice things about function notation. If we say f of negative 1, what this means is wherever there's an x, I just put a negative 1 there. So wherever there's an x in this little equation, we're going to put a negative 1. So this is 3 minus 2 times negative 1. You'll notice that they've done the work here, and we get out a 5. So this means f of negative 1 is equal to 5. Here's what's nice about it. You can look at it, and you can tell what the xy pair is. We plugged in an x. We got out a function value, or a y. The point that this would correspond to would be negative 1 comma 5. So when we plug in a 2, I won't look at all of these, but if I get f of 2 equals negative 1, what point does that correspond to? 2 comma negative 1. It's just a different way of writing y equals. Y is exactly the same as f of x. And notice what we have here. You plug in x, you get out y. The function value is the y value. Okay? So let's take a look at the next page. Oops. Okay, so it says, although, and let's take a good look at this because this is important. We'll see this all the time. Let's see, Sarah, would you read that next one right there down to for instance, and then I'll read the rest. So f of x equals x squared minus 4x plus 7, or we could say this would be f of t equals t squared minus 4t plus 7, and this would be g of s. Okay? We call them dummy variables. They're just names, so the name of this function would be g, and g is a function of what variable? S. So it's s squared minus 4s plus 7. In fact, all we need here is just a little placeholder. We could call it anything we want. So if I wanted to say f of a school bus, then wherever that little blob was, I just put a bus. Okay? It's just a placeholder. By convention, we usually use f of x, but we can use g of s or whatever it happens to be. So here's where it gets a little bit interesting, and you've probably seen stuff like this before. This is very easy. You're just plugging in the number 2. So you put a 2 here, here, and here. It's always a good idea. Notice the details here. Notice that they plugged in parentheses. So the negative is outside. We plugged in a 2. There's a 2 here, here, and here. And then they just do the arithmetic. This is negative 4. That's positive 8. That's 1. We combine all those. So we get g of 2 is equal to 5. What point would that correspond to on an xy plane, or in this case, an SG plane? 2 comma 5, over 2 and up 5. Let's take a look at what we get here. G of t. That means wherever there's an x, what are we going to replace it with? We're going to put a t. Notice that they've plugged in parentheses. These are good habits. So this would be negative t squared, there it is right there, 4 times t plus 4t, and the 1 doesn't have a variable, so this right here, that is the answer. By plugging in a t, you get a new rule or a new expression that represents that function in terms of a different variable. Okay? Now, let's take a look at the most interesting example right here. They want us to find g of x plus 2. So what that means is, wherever we used to have that placeholder, that variable, I think it was s on this one, we're going to put an x plus t. And here it is absolutely critical that you use a set of parentheses. So negative, whatever it was that we plugged in, squared, 4 times whatever it was that we plugged in, and then plus the 1. Notice that they squared that out correctly. Notice that in the next step, they went through and they distributed here and here. And then we're going to go through and collect like terms. So we've got a negative x squared, a 4x plus a 4x, minus 4x plus 4x. And then we put these constants together and we get this right here. And what people have to get used to is when we plug in an expression, we're going to get an expression out. Okay? You're not always going to get a number answer in math. We kind of get used to that, but that doesn't always happen. Any questions? Raise your hand if you've seen that type of substitution before. Fabulous. More than half of you. That's great. Then we should be in really good shape here. Okay, the next thing is a piecewise function. And I'll tell you from experience, many people struggle with piecewise functions. Okay? I think we talked just briefly about these before. Maybe this is the first time we've come across them in this class. But it says evaluate the function when x is equal to -1, 0, and 1. A piecewise function is exactly what the name indicates. It's a function that comes in pieces. So f of x is equal to these two expressions at different times. So how many pieces do we have here? We've got 2 pieces. This is a piece, and this is a piece. Now, how do we know when we use which one? Anybody know? It depends on what we're plugging. Yeah, go ahead, Alexis. Okay, you'll get the top one, right? Okay, so what this means is, here's how you read a piecewise function. It looks like this, or it is this function right here, whenever we're plugging in x's that are less than 0. So the first thing you have to figure out is, what are we plugging in? Let's plug in a -1. If you plug in a -1, which one of these two is true? -1 less than 0 or -1 greater than or equal to 0? The top one. This one's true, so we're going to use this one right here. So f of -1 is going to be -1. Notice that I put that in parentheses. Square that, and then add 1. So notice what we got here. We got out a 2. If we're going to do f of 0, is 0 less than 0 or is 0 greater than or equal to 0? Which one of these is true? The bottom one. So if you plug in a 0, you get 0 here, -1. That's why you get a -1 for that answer. You doing okay? If you plug in a 1, it's not less than 0, it's greater than 0. So again, we're going to use this one right here. So plug in a 1. 1 minus 1 is 0. That's why we got an answer of 0 there. Okay? That's a piecewise function. Any questions? Yeah.
How do you know
that they would give this to you. Okay? This is so think of a function as a rule. A very consistent mathematical rule. You plug in a number and it gives you exactly one number out. Okay? So this is just a more complicated rule. It's got 2 pieces, 2 functions, 2 equations that give you the y value. And you only use this one if you're plugging in numbers that are less than 0, so you'd have to be plugging in negatives. And you only use this one when you're plugging in 0 or positive. Does that work? Okay. Good question. Okay, go ahead and flip the page over. Okay, and now we want to talk about the domain of a function. And let's see, Hope, can I have you read that first paragraph really loud? Where it says the domain of a function. You got to find the page once you flip over. Okay, it's page 1, what is it, 129? Yeah, go ahead. Okay, so implied domain, usually we just assume that the domain is all real numbers. You can plug in anything you want. So from negative infinity to infinity if we wrote it in interval notation. But let's take a look at this one right here. Okay, there may be some numbers, depending on what the function, what operations the function uses, that we need to throw out. Do we need to be careful with this particular function right here? Nathan, why do we need to be careful on this one? Okay, and the big problem here is it's division. We don't want the denominator to be 0. So remember, we've talked about this. You've got to be careful with division, which this has. You can't divide by 0. You have to be careful with even roots, which are coming up next. And you also have to be careful with logarithms, which we probably won't see for a while. Okay? So this has an implied domain of all real numbers other than plus or minus 2. And why can't it be plus or minus 2? Because if you plug in a 2 or a negative 2 and square it, you get a 4. 4 minus 4 is 0. Or, take a good look at this. When would that equal 0? You should know how to solve that. That was on the last test, right? You can factor that. That's a difference of squares. What would make that denominator equal to 0? 2 from this one and negative 2 from that one. Okay? That's how we could figure that out. Okay, let's take a look at this one right here. Can you plug in anything you want? Nope. Hop. What do we have to be careful of here? You can't plug in any negative numbers. So in other words, we can only plug in numbers that are greater than 0 or equal to 0. Okay? So this one would have a domain from negative infinity to infinity as long as we didn't use plus or minus 2. Where would the domain start on this one? Start at 0 and go all the way to infinity. Okay? So notice it says defined for x greater than or equal to 0, and it's got that interval notation right there. Okay, are there any questions? Easy enough? Okay, let's take a look at the next one. It's got functions listed for us here, and it says figure out what the domain is. The domain on this one is simply all of the x's. So you'll notice that in the answer set it has a negative 3, a negative 1, a 0, a 2, and a 4. There they are right there. Let's take a look at this one right here. Lynn, do we need to be careful on this one? Yeah, what can't we plug in? Can't plug in a negative 5. So it would be all real numbers except for negative 5. On this one right here, let's think about this for just a second, because this has a description and then it has a function. Don't look down below. Think about that for just a second. It's about a sphere. A ball, right? A globe. What type of numbers can you plug into that? It's a radius. Got to be positive, right? Okay. Now let's see what they say. They say the radius has to be greater than or equal to 0. Another way of describing the positives. Okay, if we wrote it in interval notation from 0 to infinity, does anybody want to argue about whether or not we should include the 0 or not? You think it shouldn't be included? Okay. What if the radius was 0? Would you have a sphere? No. Okay. And then this last one right here, this is a bit more complicated. We want to know when 4 minus x squared is greater than or equal to 0. Anybody remember those? We did those in the last chapter, didn't we? Okay, let's factor this. This is 2 minus x, and this is 2 plus x. The number here is 2. The number here is negative 2. We had names for these. Does anybody remember what we called these? What's that? They are integers. I'll take that. When we're solving an inequality like this, we called them critical numbers. We call them critical numbers. Because what they do is they break up the x-axis into intervals that work and intervals that don't work. And as you can see right here, only this stuff in here works. So if you plugged in a number here, it wouldn't make the inequality true here, neither here, but it would here. Okay, remember doing those in the last chapter? Okay. If you don't, that might be something that you need to go back and review. Okay? Any questions there? Okay, let's keep going. It says in example 5c, this one right here, note the domain of the function may be implied by the physical context. Okay, whenever we're dealing with a real world problem, we'll have some of these. We'll talk about the real world domain. Okay, so maybe the mathematical model would work anywhere, but in the real world, it would only work for positive numbers, or maybe from 5 to 200 or something like that. Okay, we'd call that the real world domain. So they address that issue down there. Let's take a look at the application here. Okay, and Jordan, would you read that one for us, please? Example 6.
You work in the marketing department of a software company and are experiencing with a new soft drink that is slightly narrower. All implements your experimental ratio that radius storage.
Okay, so let's take a look here. It says express the volume of a can as a function of the radius r. Volume of the can as a function of the radius r. The answers are sitting right there. Okay, but you shouldn't look at those right away. It wants you to come up with a function. So we've got to think about this for just a second. You have to know how to find the volume. This is called a right circular cylinder. We can just call this a can, volume of a can. The way we figure out the volume of a can is we figure out the area of the base. Since the base is a circle, that is pi r squared. Then we multiply it by how tall it is. So the volume is pi r squared, that's the area of the base, times h. Now, we'll say this numerous times in this class. What don't we like about this? I'll ask that question a whole bunch. And what you're going to do is you're going to look over here and you're going to say, there are two variables. Doing algebra and doing functions with one variable is hard enough. I've got a variable r and I've got a variable h over here. So this is not okay. This is the right formula for a can, but this isn't the volume as a function of the radius. So here's what we take advantage of. What it said was the ratio of the height to the radius is 4. So what that means is the height is 4 times whatever the radius is. So take a look at this right here and this right here. What we don't like about this is it has two variables. Which variable can I get rid of using this relationship right here, Noah? I can get rid of the h. So you'll notice what they did is, instead of writing pi r squared h, they wrote pi r squared, and then in place of the h, they said what h equals, which is 4r, and then they just multiplied through. What's the difference between A and B? Take a good look. What's the difference between what they did for A and what they did for B? And this is a story problem, and I realize it's 8:45 in the morning. Take a look at what they started with. What did they do here? What's the difference? Who knows? Who can explain this? Okay, Noah, go ahead and give it a shot. Okay, they found the answer in terms of h instead of for r, and here's why. And this is why that terminology, that verbal description of a function is so important. It says express the volume, v, as a function of the radius. So that means we want volume on one side, v on one side, r's on the other. I've got v on one side, I've got r's and h's on the other. I didn't like the h, so I replaced it. What they replaced here was the r. And how did they do that? They took this little equation right here, which is a very simple linear equation that everybody in here can work with, and they made it look a little bit different. They said instead of saying h is 4 times as big as r, you can take that same relationship and you can say, well, you know what? If you take h and divide it by 4, I can tell you what r is. So in other words, r is 1/4 of whatever h is. So wherever there was an r, we put an h over 4. Square that, I get h to the second over 16 times h. That's why we've got h cubed, 3 h's now, divided by 16. Okay? Any questions? Verbal descriptions and word problems get a little more complicated. Usually people struggle with those. Hopefully that's not the case with you. So let's take a look at example 7. Let's see, Lynn, would you read that example there? Okay, so here's our function, and this is the path of the ball. Notice that they've graphed it here for us. This is x, this is how far it went horizontally in feet, and that's the height. Okay? So here's our function. It's not the nicest looking function. We've got this negative 0.0032 in front of it. Okay? So both x and y are measured in feet. So this is height in feet above the ground, and this is the distance horizontally that it's traveled. Okay? And it says, will the baseball clear a 10-foot fence located 300 feet from home? If this gives the height of the ball, based on how far away it's traveled, we plug in a 300. We want to figure out what the height is when it's 300. So notice what the function looks like. Wherever there's an x, we're replacing x with a 300. So we put a 300 here. It gets squared. Notice that they plugged it in parentheses. That's the right way to do it. Plus 300. That's what we're replacing x with. They do all that work, and it's 15 feet. So is it going to clear the fence? Yes, it is. Okay, are there any questions? Yeah. Because right here, that was part of the question. It said, will it clear a 10-foot fence that's located 300 feet away? So if you think of this as home plate right here, and this is 300, so let me draw a better picture here, okay? Out here at 300 feet, this is where the fence is, and they hit the ball from home plate over to here, and it goes like that. We can figure out how tall it is or how high the ball is above the ground when it's 300 feet away. If they had said, you know, the outfielder is standing at 250 feet, will he be able to catch it if he's 6 feet tall or something? Then we would have plugged in 250. Okay, so we figured that out. We knew that the important part on this ball field was 300 feet from home plate. Does that work? Okay, anything else? Sure? Okay. All right, let's see, on page 131. Okay, look at 131. Can somebody tell me something about that function right there? It's got a name. What do we call those again? Piecewise functions. Okay, how many pieces does this one have? 2. Now, if any of you are interested in going into business or finance or something like that, piecewise functions come up quite a bit, so it would be a good thing to be familiar with. Okay, what I would like you to read, what I'd like you to do is, I think we've got 2 pages left, 2 short pages. I want you to read this one right here. So read example 8. I want you to look at example 9, because how many of you are planning on taking calculus? Raise your hand if you want to get to calculus. Fabulous. That's everybody. I will love seeing that. If you see this symbol in this textbook, it means that's a calculus type skill. So I would like you to read the last 2 pages. Come tomorrow with questions. We'll do a couple of questions and a couple of problems, and then we're going to get started on 1.4. Okay? 1.2 is due tomorrow. You should work on 1.3 and do as much as you can, and I'll take questions on that tomorrow. 1.3 will be due the following day. Okay? I'd consider us done enough that you can do the assignment. Okay? Any questions? All right, have a great day.